magazine, in the year 1896, he drew attention to this problem. How carbon dioxide can warm up the whole thing. So that is the kind of thing already people have said we should be aware and so on. That is what Alvaro says, that these are some of the grades. And then of course it goes on by Ferranulli says selective interactions should be enhanced and so on. Go to the next one please. Next one please. Yeah, promote sustainable living, catalyze energy production. I am sure Professor Viswanathan is going to speak about catalysis and kind of chemistry catalysis and so on. So go to the next one please. So these are some of the 10 great practitioners of today's chemistry. Talking about the 10 great practitioners of the earlier chemistry, the earlier generation, and trying to make connection between the two and trying to draw the importance of chemistry and what chemistry should do and what kind of chemistry we should be practicing today. That is the thing. Now I want to draw your attention to another article which came in Nature sometime back. So the general thing, I think mainly dwell on that. Towards the end I will give a couple of examples about this one. Go to the next one. See, at the turn of this millennium, there is a big debate whether chemistry is going to serve any useful purpose. See, you take physicists, all the time they are worried about or they are concerned about grand challenges like the origin of the universe, Big Bang theory, Einstein, and the nature of speed of light. Even now there is some controversy about the speed of light and somebody said that Einstein has been falsified. They have found something faster than light. So such great grand challenges when people talk about it, young people are fascinated about physics. Oh, they feel, okay, when they are in the graduation stage, they feel that physics is the big thing that you must jump in and do something like that. Similarly, go to biology, they talk about grand things like what is the origin of life, what is the origin of memory, what nervous system do, how things fail, what proteins, folding, and biology. And so, biology also has got a lot of innumerable challenges. So, people are fascinated. So, as compared to physics and biology, people in between thought that chemistry is okay. It has passed its prime. Like I have passed my prime, you know. The youth is over. For 100 and odd years, it has already served the purpose. It is no longer having any more challenges. Therefore, people even gave the conclusion they can close down the departments of chemistry in the Western world. In England, they actually decided to close down some chemistry department, and then they decided to rename the department of chemistry as some name they have given. I think, what is that? Even, see, American Chemical Society, everybody knows in this field, that is the most respected society, very big society. And they thought sometime to rename it as Society for Molecular Sciences and Engineering. So the word chemistry itself is gone. To that extent people believed it, but fortunately better senses prevailed on them. So chemistry departments have not been closed anywhere. So we don't have to be afraid in this country to close down the departments of chemistry. Chemistry is alive, chemistry is kicking, and it will flourish for another millennium. Okay, take it from me. And this is the article in that regard. Nature magazine has brought out. Go to the next one. There are a lot of questions remain that chemistry has to. Only with the knowledge of chemistry can solve this. Go to the next one, please. I have listed what are the major questions to crack. How to design molecules and materials with specific functions. I have asterisked it because it is related to solid state chemistry and materials chemistry. Designing, that is the word, key word. Whether it is molecular material, design. How do we make the materials needed for the future in energy, aerospace, medicine, etc.? Again, synthesis comes into the picture. What is the chemical basis of thought and memory? How did life on Earth begin? How did we explore all the possible permutations and events in the periodic table? There are 10 to the power 40 permutations, again synthesis. Okay. Now, you see in the periodic table, we we have 100 odd elements, and you try to make permutations and combinations of these elements to make compounds. There are innumerable combinations. Your life, my life, and the life of the entire set of people, human beings on earth, will not be sufficient to explore all those permutations and combinations. Therefore, we have to understand interactions. What is the chemistry behind it? What is the role of physics? What is the role of thermodynamics? Everything we have to understand in order to meaningfully to narrow down the choices and create what we want. So the idea is chemistry is not dead. Chemistry is quite alive, and it has to be. It is only chemistry can solve. It's like, for example, this is a quote I have picked up from that article. Only chemists know how to engineer atoms and molecules. If room temperature superconductors or synthetic bacteria are ever created, it will not be physicists and biologists who make them. By implication, what it means is only chemists. I know that room temperature superconductor has not been made, but I didn't know that even a bacteria has not been synthesized so far. Okay? Bacteria has not been synthesized. If at all, a bacteria has to be synthesized in a laboratory, or of course, room temperature superconductors and kind of materials have to be synthesized, it cannot be physicists. Please, physicists don't get wrong, don't get angry with me for saying. Physicists have a role to play, I am going to say that. But the starting point of all these things, it's only chemists who know how to put things together, how to put all the atoms together, because they know the interactions, they know, the pulse of each and every element in the periodic table, they know. And that's how they can help in the synthesis of these materials. Go to the next one. Now, this again, I will go through this faster. Nature Chemistry, 2009 or something. Again, they looked at this problem of future of chemistry, and another 7 or 8, 10 great people have said synthesizing our future, powering the planet with the solar fuel, and so on. Go to the next one, please. And chemistry goes green, printing the structured feature. These are supramolecular chemistry. These are some of the issues, again, by a different set of people. Go to the next one, please. So, by going through this article, I picked up the relevant statement and modified it for my purpose, our purpose. What is the language of chemistry? It's very important. From Joe Fraser Stoddard, he's an Englishman, settled somewhere in California, very successful practitioner of molecular chemistry. He says, if you think atoms are the alphabets, okay, for the language we have the alphabets, and then the molecules are the words. You put the alphabets together, you create words. Okay? Same way you create molecules from atoms. And then those molecules, you put them together by weak interactions or whatever, you create supramolecules or supermolecules or supramolecules. They are like the phrases in the sentence that we make. And finally, it is the non-molecular solids are like the complete sentences in the language of chemistry. So, we, the solid state chemists, and Professor Indubhushan Sharma will be happy to know that complete sense of chemistry is manifested only when you make non-molecular solids. When you make just a molecule, it is like making a word. Word doesn't convey full sentence. When you make a supramolecule or supermolecule, it is like a phrase. Okay? Only when you make an extended solid, okay? And then only you see the full articulation of chemistry in the name of its structure, properties, dynamics, and these applications, etc. Okay, so I think that will give for entire generation an idea of what is chemistry and what is the role, etc. Now go to the next one. Now, there is a confusion in the minds of people, especially younger people. Now we talk about solid state chemistry, we talk about materials chemistry, what is going on, where solid state chemistry starts, where materials chemistry begins, etc. In order to define this issue, Chemistry International recently, some very famous people in the area of chemistry, materials chemistry, like Peter Day from Oxford, Len Intran, who is the editor of Chemistry and Materials, Tony West from England, they wrote an article. They try to define the words materials, solids, materials chemistry, etc. for the application for adoption in the IUPAC, International Union of Pure and Applied Chemistry. So this is how they define what is a material. The key to defining materials chemistry lies in defining what constitutes material, etc., etc. The references here, young people can go through that. See, you have a lot of solids, you have a lot of materials, but not all solids are materials. Okay, solids are materials. You call a solid a material only when the solid possesses some useful property. Okay, sodium chloride, for example, you may say it's a solid, it has no purpose, and therefore it may not be a real material. Of course, it is very useful for our body, etc. SiO2, which is there, sand and rock everywhere is there, it is a building material, therefore it serves a purpose. So, always you should ask the question, when does a solid become a material? If it becomes a material, then it serves some useful purpose. It should have some property. It could be a building material, it could be an electronic material, it could be a magnetic material, it could be anything. So, you should have this attribute of some usefulness, some practical application. Then only the solid becomes a material. That's how they are trying to define. That is, materials chemistry comprises the application of chemistry to the design, synthesis, characterization, processing, understanding, utilization of materials, particularly those with useful or potentially useful. They made a very complex sentence. You don't have to look at that, but that is for bookish purposes. So you should keep in mind, whenever you have solid, okay, ask the question whether it is going to serve any purpose. Forget about its structure, forget about other things, whether it serves some purpose. If it serves some purpose for human beings, then you can call it a material. And the chemistry that deals with that type of thing is called materials chemistry, simple-minded definition of that. So that is the international accepted definition for materials chemistry. For the next one, please. Today, to my mind at least, if you look at the material scenario today, what are all the kind of materials? There are dense materials that we have been Ramanan, Kapuri, Uma, and all other people those days, 20, 30 years when we started this work, dealing with these things. That is dense materials that has got no pores, nothing, everything is highly packed and so on. That is one kind of material, even now we are working on that. And some example I have given, LiCO2, Metal Oxides, all kinds of things. These are all dense, we call them dense material. That is the material, those kind of solids are those that solid state chemistry was concerned with the early days. Now in contrast to that, we have porous materials, equally important, zeolites, which are naturally occurring porous materials, then man-made porous materials like the MOF, metal organic framework, metal organic inorganic framework, and things like that. These are, channel structures where you can put in, there are huge pores of nanometer dimensions, angstrom dimensions, where other molecular entities can go in and out, and they have wonderful catalytic properties for separation of gases, for bringing out, specialized reactions, organic reactions, and so on. So that is a second kind of material. Third kind of material, hybrid materials. That is, you take a host and put organic thing inside, and then layered materials, etc. Nanomaterials. This is another craze or another important dimension of material chemistry that has come up in recent years. That is, you take a bulk solid. Bulk solid means however much you take a solid and keep on grinding it, the smallest dimension that you can get down to is micron. A micron is already 10,000 angstroms. Okay, but if you can reduce the size to 10 angstroms, that is what is called 1 nanometer. If you can reduce the size of the solid to 10 angstroms, that is what is called a nanomaterial. So whatever bulk material, you can render it to nano dimension. That is 10 angstrom, 10 to 20, 10 to 100, something like that. When you go to such low dimensions, you may ask what is the use of it. Because now you must understand, the surface area becomes more important and comparable to the bulk of the solid. But you keep on making that simple change, make different. So surface, mind you, is bound only by half the layer of atoms, half the set of atoms, the other half is free. Unlike an atom sitting within the bulk is surrounded by all the dimensions. So this change and the increase of surface area brings into a lot of new properties, both electronic as well as physical. The band structure itself changes. The band width becomes there. So what becomes the normal semiconductor will become a wide band semiconductor. Something. And also the mechanical properties become different. Big materials become very strong. Okay, one of the problem of materials is they have a lot of defects, and because of defects the material's strength is lower. Dislocations and things like that which bring down the strength of the material. So nano dimension confers very important and useful properties which are not present in already bulk materials. That's how the nanoscience has become very important. Dense and porous materials are entered into nano dimensions, etc. Amorphous and non-crystalline materials. You know that window pane glasses, metallic glasses, any solid can be rendered into glassy state, provided you know how to sufficiently cool the melt to lowest temperatures, very fast cooling, and so on. And when you go to amorphous state, again another set of new properties and so on emerge. So that is another glass science, its own usefulness and so on. It has been going on. But in addition to that, I have put this at the bottom to draw the attention of the people that the 2011 Nobel Prize in Chemistry has been given to so-called quasi-crystals. We never thought actually when quasi-crystals came up somewhere during the 1986 or so, the first paper appeared. It was all metallurgists in our institute were talking about quasi-crystals. That is, they make aluminum manganese alloys and they did some unusual thing. See, crystal means there is a long range order. Amorphous means there is no long range order. Simple way. How to distinguish between a crystal and amorphous material? Take a crystal and put it in a diffractometer. You will see definite crystallographic patterns, electron diffraction or X-ray diffraction patterns. You take a glass and put it in a diffractometer, you don't see such specific patterns. Okay. Now quasi-crystal is very interesting and it shows a pattern, but that pattern is not allowed by crystallography. X-ray crystallography allows certain symmetry restrictions on solids. That is, it can have 1-fold rotation, 2-fold rotation, 3-fold rotation, 4-fold rotation and 6-fold rotation axis in terms of symmetry of crystals, regular crystals. 5-fold is not allowed. But that is what Daniel Shetland saw when he made these things. It became 5-fold symmetry, 10-fold symmetry, etc. People are making fun of him, including Pauling, who was alive at that time. He is seeing some funny things, he is calling quasi-crystal, etc. Now, the circle, it has come to a full circle. The world has accepted the existence of a new material, which is in between crystalline solid and amorphous solid, and that is what is quasi-crystal. So, chemists, we have to now consider, we have to be concerned, we have to worry about it. What are these quasi-crystals? What is it? It's a new area actually, new area that we have. So, for the next one, please. Okay, I think that is the kind of general introduction I wanted to give for the area of chemistry, where we stand in chemistry today, and where materials chemistry, solid state chemistry fit into the whole scheme of things, and so on. Now, to complete the story, I think where is the organizer? Fakir Ahmad? So, can I take, with your permission, another 15 minutes? Is it allowed? Okay, because you are the boss. So, now for the next 15 minutes, I want to focus on what is it that we have been doing in my career and how inorganic, see I am basically an inorganic chemist. Those who have worked with me, they will understand. Whether it is Umar, Surya, Ramana, will understand. Because my basic training and my guru, I graduated from the Inorganic and Physical University. So my thinking goes back to inorganic chemistry, and from the knowledge of inorganic chemistry, how you can use it to make some solids and solid state chemistry, etc. So sometime back I prepared this talk. I thought about it. How some of the simple concepts that students learn, we as students learn in inorganic chemistry, how those things are becoming actually useful in the practice of solid state chemistry. Like for example, go back. Acidity and basicity. See, in solution, we know the pH scale. pH is 0 to pH 14, proton concentration, acidity and basicity of the liquids, aqueous solutions we define. The same concept of acidity and basicity is very much useful in the solid state also. We can define an acidity scale for an oxide, and on the basis of acidity basicity you can rationalize the reactivity factor. I will show some examples. And similarly, oxidation reduction is something which you learn in about the ferrous-ferric titration, cerium-3, cerium-4, dichromate and all. Simple ideas about oxidation reduction. How you can make use of this knowledge of oxidation reduction chemistry in our solid state chemistry practice. Similarly, you have crystallinity, untunnel distortion, mixed valence, electron transfer, metal-metal bonding. These are all concepts in regular BSc level or MSc level chemistry that we learn, and each one of these concepts find very important use in the practice of materials and solids. Go to the next one. Now, of course, this is the one that I used to tell. The first for materials, new materials, and I don't want to spend too much time. What are the kinds of materials that you want? Materials that are super hard, materials that don't expand on heating, materials that split water, materials that can convert methane to hydrogen, etc. etc. So, for all kinds of applications we need materials. Go to the next one. Now again, few materials for advancing technology, super hard materials, zero temperature expansion, all these important properties and what are the prototypical examples picked up from current literature, they are made oxides. Go to the next one please. Now again, the same property versus example of some of the materials of current importance. Go to the next one. Now, if you look at inorganic materials, there is a dichotomy, there is a catch. Most of the materials that we see on the planet Earth are of inorganic origin, starting from the rocks, the sands, and the clays. All are inorganic. Of course, there are a few organic things. All non-living things that you find on the planet Earth are inorganic origin. And similarly, all those examples that I have given for application in today's technology are also inorganic materials. Most of them are 99% you can say they are inorganic materials. So that's why I said inorganic materials are ubiquitous. Most of the minerals on this planet are inorganic materials. But the catch is they are thermodynamically stable materials. This is what I want to bring to the attention of especially younger people. Don't avoid physical chemistry. Physical chemistry you must learn if you want to be a good practitioner of inorganic chemistry, solid state chemistry, or even organic chemistry. Without physical chemistry you can't be a successful practitioner. Because when you take any solid, any molecule or whatever, the question arises whether it is thermodynamically stable. All these things that we are talking about, there are thermodynamically stable things. But then you look at the technologically important materials of today that I have given the example, they are all metastable. That is where Mother Nature has put a catch on us. What we want is not available readily in the planet Earth because they are metastable. What is available is actually thermodynamically stable materials like rock, sand and silica. So they are useful but not vital. So if you want any useful material, want to make any useful material, electronic material or whatever, all batteries and this and that, you have to go to the laboratory and you have to make it yourself because they are not thermodynamically stable. You have to kinetically stabilize them. That is where the knowledge of chemistry, whatever you have learned, kinetics versus thermodynamics, metastable materials versus stability, all these issues come into the picture. So that's what I highlighted. Many of them are metastable cases. Go to the next one please. So this is the scope of solid state chemistry. Crystalline solids deals with that. That is the compounds formed from both metals and non-metals in the periodic table. You have all these what is the non-metallic elements. You have tetralides, peptides, chalcodenides, halides. The scope is really very large. But all the time, at least most of the time we are dealing with oxides, most easy thing, available readily, Oxygen is there in the atmosphere. You put any metal, heat it, it forms an oxide which is quite stable, etc. Go to the next one, please. So synthesis becomes crucial for the development of materials because you need to control thermodynamics, various reasons. Go to the next one. Conventional synthesis of heating at high temperature, heating, etc. gives thermodynamic stable. These are well-known things. Go to the next one. So we need to have kinetic control. Go to the next one. Chimie do. This is a French word which actually means gentle chemistry. Whatever you do chemistry in solid state, you should not use brute force. Brute force means put things together, heat, grind, etc. That will give stable materials. This is okay, but all the time we don't use that. So we have to have this gentle chemistry where knowledge of physical chemistry, thermodynamics, everything will be used. That is how we have to open up our mind. So the entire field of chemistry, if you want to synthesize meaningful things, go to the next one, please. Now, how to synthesize metastable solids? This is something which I have learned from Arthur Slade and DuPont and so on. He said there are 3 different proofs, etc. These are textbook materials by now. So, go to the next one, please. Now, this is what he came up with some years back. How this Oswald step rule is useful in understanding the metastability using zeolite synthesis as an example. You start with the gel and you do the reaction of crystallization of a gel as a function of both temperature and time. Temperature and time are the 2 variable factors. I didn't know how to, in a 2-dimensional plot, you cannot separate temperature and time. Actually, you need to have a 3-dimensional plot to put temperature and time along with the thermodynamic stability, and when it starts crystallizing, you get gradually microporous materials, less microporous, still less microporous. Finally, you get silica for dense phase. This is what is called Oswald step rule. And people didn't understand the basis of Oswald step rule. I think something people do understand now, the basis of Oswald. That is, what is the catch there is, take a gel and crystallize under hydrothermal or whatever condition. Or you take a melt and crystallize it also. Anything, or you take a solution and crystallize. Supposing there are half dozen phases in the particular system, the one that forms first is not the thermodynamically stable phase. The one that forms first is the least thermodynamically stable phase. That is a dichotomy. So, kinetics has a role in stabilizing the metastable phase. So, we have to understand the process of synthesis, control of temperature, control of time. Now, add to that another dimension, control of pressure. Because I have not given pressure as a dimension, high pressure. People do the reactions now. So, by playing around with these 3 parameters, time, temperature and pressure, you can access lot of metastability. That is the message that I want to give. And of course, we are doing still research on that. We are trying to understand the kind of metastability. I have some fancy ideas. We try to prove that what is the origin of metastability and what is the physical chemistry basis of that, etc. I think probably this is not the occasion to explain on that. Go to the next one, please. Now, this is the one that is a textbook material again now. What is the difference between molecular chemistry and solid state chemistry? These are textbook example. I am sure all these people who are professors in IITs and the universities, they will be teaching these things to the students. Go to the next one, please. Now, this I want to give, always I try to focus on that. This came on Nature some time back, color paint. That is, although I said that you mix things and heat it and synthesize, etc., people have to be very careful because chemicals in the bottles are like serpents, snakes. Okay, you have to be careful. When you open a chemical in the laboratory and try to put 2 chemicals together, it can be quite catastrophic and dangerous to the person who is doing the reaction. Because we don't know the reactivity. Here is one example of MOS2, MOCl5 with the sodium sulfide. These 2 compounds are quite stable if you put them together in the bottle separately. But the moment you put them together, this is the reaction that takes place, giving MOS2, sodium chloride and some sulfur. Along with that, so much of energy is released, 230 kilocalories per mole in a short time. That is an important thing. Instantaneously, energy is released. And that energy can scale levels, 1600 degree Kelvin. So when you mix and try to grind or do something, the whole thing will burn and come on your face. So you have to be very careful. It will be very dangerous, catastrophic. That is the attention of this, the work of Vaidya and Anand. You see that they are mixing things in an agate model and how within a fraction of a second, these are microsecond frames, within a fraction of a second things are exploding. So mind you, students especially, ask your supervisor when you are trying to put things together, understand before you really mix and heat things. Okay, go to the next one please. Okay, acidity, basicity, bronze acidity, metal ions, aqueous solution, these are all well known. I'm going to finish now. One example. Go to the next one. Now, similar to what we talk about acidity and basicity in the solution media, namely pH and pKa scales for amines and acids, for solids also, people have proposed acidity basicity scales for all the oxides. They are given. Okay, like Li2O or N2O is the most basic oxide. Re2O, C2O7 or WO3, these are most acidic oxides. Okay. We use this knowledge to do some chemistry. Go to the next one please. Now some time back we did that. We took Li2CO4 and reacted with several binary metal oxides. Go to the next one please. When we do that, a very highly acidic oxide like Re2O7 reacts with Li2CO4, forming Na3ReOH. Copper oxide is brought. Normally we expect when you put them together, a solid comprising all these elements will form addition product. But what happens here is a metathesis reaction where copper oxide is thrown out, because that is because lanthanum oxide highly basic, rhenium oxide highly acidic. Therefore, this is a kind of acid-base reaction product. Acid and base in solution, you put them together, forms a salt. That is the kind of situation. Copper oxide is unwanted there, is thrown out. Similarly, Li2CO4 plus MOO3, another acidic oxide, you get this product, copper oxide is thrown. P2O5, also quite acidic, you get this product, copper oxide thrown out. But by the time you come to TiO2 is sort of uncoated, not quite acid, not quite basic, and Li2CO4 reacts with the TiO2 to give what is called addition product. And of course, this also MNO will use that. Go to the next one please. So, these are wonderful things that we learn, etc. Now, can you go back and forward? Go back. Go forward. Go forward. Okay. This is an early example of soft chemistry that we did, and the man who did, an important person who contributed to this, is sitting in the audience. Where is he? I can put a red light on his face. Professor Ramanan. Okay. So, you know this MOO3 and WO3 are two reluctant solids to form solid solution because they have two different structures. Working with Professor C.N.R. we found a way of bringing them together by a soft chemistry movement. Okay, go back now. Go back. Yeah, look at the crystal structure of this WO3, that is MOO3. They are quite different structures, therefore you cannot put them together to form a solid solution by conventional means. But then you look at their hydrates and dihydrates, they have similar structure, isostructure. This one idea about the structural similarity of WO3 and MOO3 hydrates gave us the clue that you can make the hydrate solid solution, then simply dehydrate it, you get the solution. Go to the next thing, go to the next one, and that's what we did. And I think, I don't know, Supernath is an author of this paper, Ramanan. Yeah, he helped us to look at the electron microscopy and all that. So that became an important publication in Journal of Chemical Communication. So with a little bit of imagination and understanding of structural reactivity, you can come up with new solids, new synthetic forms. Okay, now go to the next one. Yeah, this is again, whole lot of other soft chemistry things that we have made with after some other subsequently based on perovskites, root oil, and etc. Go to the next one, please. Next one, please. Yeah. See this perovskite. Those who are working in solid state chemistry of the oxides cannot escape perovskites. This is simple based, etc. You can cut them into various kinds of layered solids. We call them diode Jacobson, Joulson copper, aruminous, and so on. Some sliced perovskite structures. You are familiar. Next one, please. Then Uma Asantachet also is here in the camera, working with me sometime back, years back. We have cut the perovskite structure in a different way. Cut the perovskite, three-dimensional perovskite structure to view layered structure in a different way. The idea is very simple. You take this kind of composition A, Li, Sr, N2, M49. M is a divalent metal atom, niobium is pentavalent, and you choose two alkali metal atoms. One a small alkali like sodium, another one a large alkali like cesium. You make this kind of isocomposite. Compositions are the same. When you put them together with the sodium, you get a three-dimensional perovskite structure. With the cesium, you get a two-dimensional structure. Go to the next one. So this is a kind of X-ray diffraction patterns for sodium compounds, simple perovskite structure. When you go to cesium, typical of a layered solid, and people wouldn't believe just if you give these curves.